The laws of science or scientific laws are statements that describe or predict a range of phenomena behave as they appear to in nature. The term law has diverse usage in many cases: approximate, accurate, broad or narrow theories, in all natural scientific disciplines. An analogous term for a scientific law is a principle. Scientific laws summarize a large collection of facts determined by experiment into a single statement, can usually be formulated mathematically as one or several statements or equation, or at least stated in a single sentence, so that it can be used to predict the outcome of an experiment, given the initial, boundary, and other physical conditions of the processes which take place, are strongly supported by empirical evidence. They are scientific knowledge that experiments have repeatedly verified. Their accuracy does not change when new theories are worked out, but rather the scope of application, since the equation representing the law does not change. As with other scientific knowledge, they do not have absolute certainty, and it is always possible for a law to be overturned by future observations. Are often quoted as a fundamental controlling influence rather than a description of observed facts. For example, the laws of motion require that laws differ from hypotheses and postulates, which are proposed during the scientific process before and during validation by experiment and observation. These are not laws since they have not been verified to the same degree and may not be sufficiently general, although they may lead to the formulation of laws. A law is a more solidified and formal statement, distilled from repeated experiment. Although the nature of a scientific law is a question in philosophy and although scientific laws describe nature mathematically, scientific laws are practical conclusions reached by the scientific method. They are intended to be neither laden with ontological commitments nor statements of logical absolutes. According to the unity of science thesis, all scientific laws follow fundamentally from physics. Laws which occur in other sciences ultimately follow from physical laws. Often, from mathematically fundamental viewpoints, universal constants emerge from scientific laws. Conservation laws equals conservation and symmetry equals, most significant laws in science are conservation laws. These fundamental laws follow from homogeneity of space, time and phase, in other words symmetry. Noether's theorem: any quantity which is a continuous differentiable symmetry in the action has an associated conservation law. Conservation of mass was the first law of this type to be understood, since most macroscopic physical processes involving masses, for example collisions of massive particles or fluid flow, provide the apparent belief that mass is conserved. Mass conservation was observed to be true for all chemical reactions. In general this is only approximative, because with the advent of relativity and experiments in nuclear and particle physics, mass can be transformed into energy and vice versa, so mass is not always conserved, but part of the more general conservation of mass energy. Conservation of energy, momentum and angular momentum for isolated systems can be found to be symmetries in time, translation, and rotation. Conservation of charge was also realized since charge has never been observed to be created or destroyed, and only found to move from place to place. Continuity and transfer equals, conservation laws can be expressed using the general continuity equation can be written in differential form as whereas some quantity per unit volume, J is the flux of that quantity. Intuitively, the divergence of a vector field is a measure of flux diverging radially outwards from a point, so the negative is the amount piling up at a point, hence the rate of change of density in a region of space must be the amount of flux leaving or collecting in some region. In the table below, the fluxes, flows for various physical quantities in transport, and their associated continuity equations, are collected for comparison. More general equations are the convection-diffusion equation and Boltzmann transport equation, which have their roots in the continuity equation. Laws of classical mechanics equals principle of least action equals. All of classical mechanics, including Newton's laws, Lagrange's equations, Hamilton's equations, etc., can be derived from this very simple principle. Where is the action? The integral of the Lagrangian of the physical system between 2 times T1 and T2. The kinetic energy of the system is T, and potential energy is V. The configuration of a system which has n degrees of freedom is defined by generalized coordinates q equals. There are generalized momenta conjugate to these coordinates, p equals, where the action and Lagrangian both contain the dynamics of the system for all times. The term path simply refers to a curve traced out by the system in terms of the generalized coordinates in the configuration space, that is the curve q, t, parameterized by time. The action is a functional rather than a function, since it depends on the Lagrangian, and the Lagrangian depends on the path q, t, so the action depends on the entire shape of the path for all times. Between two instants of time, there are infinitely many paths, but one for which the action is stationary is the true path. The stationary value for the entire continuum of Lagrangian values corresponding to some path, not just one value of the Lagrangian, is required. Notice L is not the total energy of the system due to the difference, rather than the sum. The following general approaches to classical mechanics are summarized below in the order of establishment. They are equivalent formulations. Newton's is very commonly used due to simplicity, but Hamilton's and Lagrange's equations are more general, and their range can extend into other branches of physics with suitable modifications. From the above, any equation of motion in classical mechanics can be derived. Corollaries in mechanics, Euler's laws of motion, Euler's equations, corollaries in fluid mechanics, equations describing fluid flow in various situations can be derived, using the above classical equations of motion and often conservation of mass, energy and momentum. Some elementary examples follow. Archimedes' principle, Bernoulli's principle, Poisson-Euler's law, Stokes' law, Naviero-Stokes equations, Farquhar-Copyright-Enns law. Laws of gravitation and relativity. Modern laws special relativity. Postulates of special relativity are not laws in themselves, but assumptions of their nature in terms of relative motion. Often two are stated as the laws of physics are the same in all inertial frames, and the speed of light is constant. However, the second is redundant, since the speed of light is predicted by Maxwell's equations. Essentially there is only one. The said postulate leads to the Lorentz transformations the transformation law between two frame of references moving relative to each other. For any four-vector. This replaces the Galilean transformation law from classical mechanics. The Lorentz transformations reduced to the Galilean transformations for low velocities much less than the speed of light c. The magnitudes of four vectors are invariants, not conserved, but the same for all inertial frames. In particular, if A is the four momentum, the magnitude can derive the famous invariant equation for mass energy and momentum conservation, in which the mass energy equivalency equals mc2 is a special case. General relativity. General relativity is governed by the Einstein field equations, which describe the curvature of space-time due to mass energy equivalent to the gravitational field. Solving the equation for the geometry of space-warp due to the mass distribution gives the metric tensor. Using the geodesic equation, the motion of masses falling along the geodesics can be calculated. Gravita magnetism. In a relatively flat space-time due to weak gravitational fields, gravitational analogues of Maxwell's equations can be found. The GEM equations, to describe an analogous gravitomagnetic field. They are well established by the theory, and experimental tests form ongoing research. Classical laws Kepler's laws, though originally discovered from planetary observations, are true for any central forces. Thermodynamics. Newton's law of cooling, Fourier's law, ideal gas law, combines a number of separately developed gas laws. Boyle's law, Charles's law, Gay-Lussac's law, Avogadro's law, into one. Now improved by other equations of state, Dalton's law, Boltzmann equation, Carnot's theorem, Kopp's law. Electromagnetism. Maxwell's equations give the time evolution of the electric and magnetic fields due to electric charge and current distributions. Given the fields, the Lorentz Force Law is the equation of motion for charges in the fields. These equations can be modified to include magnetic monopoles, and are consistent with our observations of monopoles either existing or not existing. If they do not exist, the generalized equations reduce to the ones above. If they do, the equations become fully symmetric in electric and magnetic charges and currents. Indeed, there is a duality transformation where electric and magnetic charges can be rotated into one another, and still satisfy Maxwell's equations. Pre-Maxwell laws, these laws were found before the formulation of Maxwell's equations. They are not fundamental, since they can be derived from Maxwell's equations. Coulomb's law can be found from Gauss' law and the Biot-Savart law can be deduced from Ampere's law. Lenz's law and Faraday's law can be incorporated into the Maxwell-Faraday equation. Nonetheless, they are still very effective for simple calculations. Lenz's law, Coulomb's law, Biot-Savart law, other laws, Ohm's law, Kirchhoff's laws, Joule's law. Photonics, classically, optics is based on a variational principle. Light travels from one point in space to another in the shortest time. Fermat's principle, in geometric optics, laws are based on approximations in Euclidean geometry. Law of reflection, law of refraction, Snell's law, in physical optics, laws are based on physical properties of materials. Brewster's angle, Malus's law, Berer-Lambert law. In actuality, optical properties of matter are significantly more complex and require quantum mechanics. Laws of quantum mechanics. Quantum mechanics has its roots in postulates. This leads to results which are not usually called laws, but hold the same status, in that all of quantum mechanics follows from them. One postulate that a particle is described by a wave function, and this satisfies a quantum wave equation, namely the Schrödinger-Dingo equation. Solving this wave equation predicts the time evolution of the system's behavior, analogous to solving Newton's laws in classical mechanics. Other postulates changed the idea of physical observables. Using quantum operators. Some measurements can't be made at the same instant of time, particles are fundamentally indistinguishable. Another postulate. The wave function collapse postulate, counters the usual idea of a measurement in science. Radiation laws, applying electromagnetism, thermodynamics, and quantum mechanics, to atoms and molecules. Some laws of electromagnetic radiation and light are as follows. Stefan Boltzmann law, Planck's law of black body radiation, Wien's displacement law, radioactive decay law. Laws of chemistry. Chemical laws are those laws of nature relevant to chemistry. Historically, observations lead to many empirical laws, though now it is known that chemistry has its foundations in quantum mechanics. Quantitative analysis. The most fundamental concept in chemistry is the law of conservation of mass, which states that there is no detectable change in the quantity of matter during an ordinary chemical reaction. Modern physics shows that it is actually energy that is conserved, and that energy and mass are related. A concept which becomes important in nuclear chemistry. Conservation of energy leads to the important concepts of equilibrium, thermodynamics, and kinetics. Additional laws of chemistry elaborate on the law of conservation of mass. Joseph Proust's law of definite composition says that pure chemicals are composed of elements in a definite formulation. We now know that the structural arrangement of these elements is also important. Dalton's law of multiple proportions says that these chemicals will present themselves in proportions that are small whole numbers. Although in many systems the ratios tend to require large numbers, and are frequently represented as a fraction. More modern laws of chemistry define the relationship between energy and its transformations. Reaction kinetics and equilibria. In equilibrium, molecules exist in mixture defined by the transformations possible on the timescale of the equilibrium, and are in a ratio defined by the intrinsic energy of the molecule. The lower the intrinsic energy, the more abundant the molecule. Le Chatelier's principle states that the system opposes changes in conditions from equilibrium states, that is, there is an opposition to change the state of an equilibrium reaction. Transforming one structure to another requires the input of energy to cross an energy barrier. This can come from the intrinsic energy of the molecules themselves, or from an external source which will generally accelerate transformations. The higher the energy barrier, the slower the transformation occurs. There is a hypothetical intermediate, or transition structure, that corresponds to the structure at the top of the energy barrier. The Hammond-Euler postulate states that this structure looks most similar to the product or starting material which is intrinsic energy closest to that of the energy barrier. Stabilizing this hypothetical intermediate through chemical interaction is one way to achieve catalysis. All chemical processes are reversible. Although some processes have such an energy bias, they are essentially irreversible. The reaction rate has the mathematical parameter known as the rate constant. The Annias equation gives the temperature and activation energy dependence of the rate constant, an empirical law. Thermochemistry, DeLonghi Petit law, GIBBSA Helmholtz equation, Hess's law, gas laws, Raoult's law, Henry's law, chemical transport, Fick's laws of diffusion, Graham's law, Lamb equation. Geophysical laws, Archie's law, Buys-Ballott's law, Birch's law, Peale's law. See also, List of laws, list of scientific laws named after people. Notes. External links, Physics Formulary, a useful book in different formats containing many or the physical laws and formulae. Formulae.com, website containing most of the formulae in different disciplines.